All right, this is 2016, number 7. This is the last question on the 2016 exam from 3 or 4 years back. This is a simple titration calculation. It's a simple enough problem that people should have scored better on it than they did. It has a little sig fig thing at the beginning, which scares everybody to death, even though it's pretty simple. So what we've got here is a monoprotic acid. We have 25 mils of it. We are trying to find the concentration of it by titration using a standardized solution of base. Standardized solution means a known concentration of base. So our base has a known concentration of 0.110 molar in our burette, and we are putting that 25 mils of acid underneath the burette, and then we are dripping in the base until we reach that equivalence point, given to us through a pH probe or some kind of, in this case, appropriate indicator. And so what we got in A is the initial burette reading and final burette reading, and they're simply asking us what volume of NaOH was delivered to the flask. It is a significant figure problem on 7A. You have to record these volumes with the correct number of significant digits. So like anything else, it's final minus initial. So volume final minus volume initial will tell us the volume of, in this case, the NaOH. That's what we're looking at. So here's our initial volume. These things are accurate to the tenths place. So 5.123 I can see for sure, and then we have to guess 1 digit beyond that. So we go to 1 digit beyond the known digit, and so here, and make sure, look at this is 5 and this is 6. It's shocking how many people will call this 6 point something because the volume's above the 6. It's in between 5 and 6. Be careful here. And so this is 5.65-ish is the initial volume. Milliliters is what I got. Now, could you have 5.64 or 5.66? Sure. Don't sweat that last digit too much. That's close enough. Good. And then we need our final volume. They show us the burette and they give us the final volume down here. And if you zoomed in on this thing falls right at 37.123. And so this volume final will be 37.3. You know it's a 3, and so you guess the next digit. That next digit for me is a 0. And so I got 37.30. Forgive me for not sticking milliliters in there. Minus 5.65 milliliters, and that will tell me the volume of the base that came out of those burettes. And in this case, if you subtract those off, so not only do you have to read them to the hundredths place, reading the thing right, when you subtract sig figs, you go to the least accurate place value. So you've got to go all the way to hundredths place when you subtract them. Multiplication, division, it's whatever has the least sig figs. So addition, subtraction, it's the least accurate place value. So this guy is going to be 31.65. You got to go all the way to the hundredths place milliliters. Tougher than it looks. You got to really understand some sig figs to get that answer right. So 31.65. That's just 1 point there. It's just a subtraction problem. Sig figs make it a lot more difficult. And so B says, based on the given information of part A, determine the value of the concentration of acid that should be recorded in the student's lab report. And so anytime you're doing a titration, when you reach the end point or the equivalence point, the moles of A are going to be equivalent to the moles of B. And so to do that, in this case, we have molarities and volumes. Molarity and volume of the acid will be equivalent to molarity times volume of the base. Molarity times liters gives us moles, and so moles equal moles is what we're after here at the equivalence or endpoint. Good. And so acid-wise, we are finding in part 2 the concentration of the acid. That's our unknown, molarity of the acid. We have the volume of the acid. They gave it to us at the very beginning of this problem. They told us the volume of the acid is 25.0 milliliters. The base was the standard solution. If you look up at the top of the question, it gives us the concentration of the standard solution is 0.110 molar for the base. And we just calculated the volume of the base, 31 0.65 milliliters. That's it. The moles of that are going to be equivalent to the moles of this. Now this is actually millimoles because we're working in milliliters, but you could switch them both to liters if you want. Because it's proportional to each other, the unit there doesn't matter as long as they're the same. When we calculate that molarity of acid, there are 3 digits here for the base molarity, and so I'm giving it 3 digits for the molarity of the acid, and that molarity of the acid is 0.139 molar. That's the answer to the molarity of the acid. And then the last part on here, in a second trial, the student accidentally added more sodium hydroxide to the flask than was needed. They went past the equivalence point. Would this error increase, decrease, or have no effect on the acid concentration for the second trial? Justify your answer. This student dropped too much base in. If we look back at this part B, if we added more volume of base by accident, that gives us more or additional moles of base when we calculate this, which means we're going to have calculated additional moles of acid. That volume's not changing, so the molarity would have to increase. So part C, the calculated, it's not the actual concentration, it's the calculated concentration of acid increases because additional volume of base causes higher calculated moles of base and therefore higher moles of acid. That's it. You actually get 2 points. They're increasing the calculated acid concentration. Answer the question, because additional volume of base causes higher calculated moles of base and therefore higher moles of acid. And that's it. That's number 7 on 2016.